I am Jinita, Assistant Professor, Department of Computer Science, KCS Kasinagar College. In this video, we are going to see about deadlock in operating systems. In this video, we can see the deadlock problems, system models, deadlock characteristics, resource allocation graphs. Let's see deadlock problems. What is deadlock? A set of blocked processes, each holds a resource and waiting to acquire a resource held by other process in the set. This is a deadlock. Let's see the example. System has two disk drives, resource 1 and resource 2, and we have two processes, process 1 and process 2. Each hold one disk drive and each need another one. This is a deadlock. See the picture. Here we have two processes and two resources. Process 1 is holding the resource resource 1 and it is waiting for the resource R2, and likewise process 2 is waiting for R1 and it holds the resource R2. In this case, both the process is not able to finish the process as it is waiting for the other resource. This is deadlock. Let's see the real life example. Bridge crossing. Here you can see the bridge. It has a narrow bridge which at a time one vehicle may be crossed in either direction. Traffic only in one direction at each moment in a time. Each section of bridge can be viewed as a resource. If the deadlock occurs, it can be resolved if one car backup, that is preemit resource and rollback. Several cars may have to back up if the deadlock occurs. Then starvation problems occur. System model. For the purpose of deadlock discussion, a system can be modelized as a collection of limited resources that can be divided into different categories and allocated to the variety of processes, each with different requirements. The resources are memory, printer, CPU, open file, etc. It is denoted as R1, R2 likewise. Each resource type R1 has W1 instance. In normal operation, a process must require a resource before using it and release it when finished. That is, request, use, release. Request. If the request cannot be granted immediately, the process must wait until the resource request to become available. Use. The process make use of the resource such as printing to the printer and reading from a file. Third operation is release. The process releases the resource allowing to be used by other process. It is release. Next, we can see deadlock characteristics. Deadlock can arise if four conditions held simultaneously. First is mutual exclusion, second is hold and await, non-primitive, and last one is circular wait. Let's see one by one. Mutual exclusion. Only one process at a time can be used a resource, that is mutual exclusion. Next, hold and wait. A process hold at least one resource, it waiting to acquire the additional resource held by other process. Next is non-primitive. A resource can be released only voluntarily by the process holding it after that process has completed its task. And the other one is circular wait. Thus exists a set P1, P2 up to Pn, it the waiting process such that P0 is waiting for the resource that is held by P1, P1 is waiting for the resource that is held by P2. It goes on up to Pn-1 is waiting for the resource that is held by Pn, and Pn is waiting for the resource that is held by P0. This is circular wait. If the four condition is held simultaneously, deadlock will occur. Resource allocation graph, a set of vertices V and set of edge E. The vertices V is partitioned into two types, that is P. Set of P consists of all processes in the system. R is a set of resources consist of all resource type in the system. The edge is also partitioned into two types, request edge and assignment edge. The direct edge between process to the resource is request edge. The assignment edge is nothing but the direct edge between resource and the from the resource to the process. Here you can see the pictorial representation of resource allocation graph. Process is represented by the circle. Resource is represented by the square. You can see the dots inside the square. This is an instance of the resource. Then request edge is represented as PI request instance of RJ, that is arrow from process to resource RJ. Next, we can see the assignment edge. The process P1 is holding the instance of Rj. You can see the arrow from Rj to Pi. Example of resource allocation graph. We already saw deadlock. What is deadlock? A set of blocked processes, each hold a resource and waiting to acquire the resource held only by other processes in the set. In this diagram, we can see three processes and four resources. P1, P2, P3 are the process and R1, R2, R3, R4 are the four resources. If P1, P2 are deadlocked, does the system has deadlock? No, there is no deadlock here, as P3 is a process which have the resource R3. If after finishing P3, resource R3 is released by P3, then the P2 is finished and P1 is finished. So in this diagram there is no deadlock. Resource allocation graph with a deadlock. Here we can see the same diagram, but there is one extra request edge from the P3 to PR2. So here this request edge make the deadlock. Graph with a cycle but no deadlock. If the graph contain no cycle, then there is no deadlock. If the graph contain a cycle, if only one instance per resource type, then deadlock. If the several instances per resource type, it is possible of deadlock. It is not sure that deadlock is always occur. Thanks for watching. Let's see in another video.